Hi everybody, I hope you guys are having a wonderful day today. So our lesson today is about base N numeration systems. So the number system that we use is base 10, but we're going to talk about how it will work if you have other bases instead. So in our last lesson, we talked about several different numeration systems that have been used in the past. And our current numeration system that we use is the Hindu Arabic numerals. So the way that Hindu Arabic numerals work is you have 10 different digits or 10 symbols that are listed here. And we use these 10 symbols and write them in specific orders to communicate the different numbers that we use in our modern number system. So one of the characteristics of the Hindu Arabic system is that we group our numbers by tens. So we go like 1, 2, 3, 4, 5, 6, 7, 8, 9. And then once we get to the 10, we change place values and we write it as 1, 0. Then, you go 11, 12, 13, all the way up to 20, and then 30, 40, 50, 60, 70, 80, 90. And then once you get up to 99, then you move on to the next place value. And then once you get up to 999, then you go to 1,000 and so on. So one of the things that can be really useful for helping students understand how our modern day numeral system works is to use base 10 blocks. So a base 10 block set looks kind of like this. And basically you have all of these little unit blocks. And then if you have 10 unit blocks stuck together, it creates a rod or like a 10 rod. And then if you stick 10 of these rods together, it makes a 100 plate. And if you stick 10 100 plates together, it makes a 1,000 block. And you can buy like physical blocks, or you can also use applets on your iPad. So if you're ever working like one-on-one with students, and especially if they're like a kinesthetic learner, using the physical blocks can be really helpful. But if you're teaching an entire class, that can sometimes be a classroom management nightmare. So I really like using an iPad and just projecting the image up on the screen. But you can do it basically however it works in your classroom with your classroom management style. So base 10 blocks are really useful, and you can also make this a little bit more abstract by using a chip abacus. So a chip abacus is basically when you have like a poster or a piece of paper or something that's blocked off into a ones column, a tens column, and a hundreds column, and you could also do a thousands column if you want to. And then you use different chips to represent how many blocks you have. So I would recommend starting off with the base 10 blocks, but as you get into bigger numbers that are more clunky to actually use the blocks for because there's just a lot of them, you can simplify it by using different colors of chips to represent the blocks. So they're kind of related, but the base 10 blocks, I would recommend starting with those when you're teaching your students because they physically show the different sizes of the different amounts. Like the ones are just going to be little blocks, but the tens will be big blocks and the hundreds even bigger and so on. Versus with the chip abacus, your little chips are all going to be the same size. So you should probably start by using the base 10 blocks, and then you can abstract it to be a chip abacus. So this is something that I would really recommend using whenever you're introducing a new concept, because it's going to help the students conceptually understand how it works instead of just memorizing facts. So one of the things that is often taught to help students understand how the base 10 number system works is to write numbers in expanded form. So expanded form is basically when you take the number in each place value and you write it out and show what those place values represent. So if you have 82,604, you would basically say, okay, well, I'm going to have 8 times 10,000 because I have an 8 in the 10,000 spot. Then the 2 in the 1,000 spot is written as 2 times 1,000. The 6 in the 100 spot is written as 6 times 100. The 0 in the 10 spot is 0 times 10. And the 4 in the 1 spot is written just as 4. And sometimes, depending on your textbook, this can also be written as 80,000 plus 2,000 plus 600 plus 0 plus 4, or sometimes they don't even write the 0, it's just like this. But writing out numbers in this way can really help students understand what the number actually means. And it can also help them when you're looking at the names of the different numbers. So when you're writing out the names of numbers, you know, we have our standard base digits, 0, 1 through 9. And then we have 10. And these two numbers are actually kind of like weird. Like they don't really follow a specific pattern. So after 10, we have 11 and then 12. And then after that, it does follow a pattern because 13 and 14 and 15 and 16 and so on are basically like 3 plus 10 or 4 plus 10. And you can kind of see that in the way the word is written. 14 is 4 and 10. And then once you get up to 20, then the pattern becomes even more consistent because you have 21, 22, 23, and so on and so forth. And 35 is 3 10s and 5 1s and so on, all the way up until you get to 100. And then you just continue adding on place value. So the way that you would write a number like this is you would say, I have 1,300s and then 74. And that's the way you would write a number like this. Or if you get a really big number like this one, you would have 23,100. And when you get to really, really big numbers, the place values are kind of grouped into groups of 3. So if you had a huge number like this one, you basically have your 3 like base place values, like your 1s, 10s, and 100s. And then after that, you have your thousands and your millions, your billions, and your trillions. So the way that you would read this number is basically in groups of 3. So I would say I have 744 trillion, 210 billion, 898 million, 564,798. And that's how you would describe a large place value like this. And I believe usually in elementary school, you don't really get any higher than millions. But sometimes kids will be curious and they'll wonder what comes after millions. And so you can Google this if your students ever ask you this. But there is a specific pattern to how it goes. So you have millions, and then you have billions, and trillions, and quadrillions, and quintillions, and sextillions, and septillions. And if you notice, the root words in these place values basically match the numbers. So like bi means 2, tri means 3, quad means 4, quin means 5, sextillion is 6, septillion is 7, octillion is 8. And basically they follow this root word pattern up until the decillions, because deci means 10, like decimals is when you split things up into 10. And then after that, there's more patterns after that. So like you have undecillion or duodecillion or tridecillion, or however you say that word. I don't even know how to say that. But that's kind of how the place values build on themselves. So if you ever have a curious student that's like, what comes after this? You can always look it up and see what the names of the place values are after that. Now for the rest of this video, I'm going to be talking about how numeration systems with other bases work. So remember, a number is an idea of an amount of something, and a numeral is a symbol that we use to represent that amount. So in our base 10 numeration system, we have 10 different symbols that we use to represent amounts. So we have the symbol 0, which represents nothing. Then we have the symbol 1, which represents one item. And so that symbol of a line is representing the amount of having one item. And then we have the symbol 2, which represents 2 items. And then we have the symbols 3, 4, 5, 6, 7, 8,
and 9 that represent those corresponding numbers of items. So here I've got 2 items, then 3, 4, 5, 6, 7, 8, 9. And so these symbols are representing the amounts that I've shown visually with these base 10 blocks. Now, the reason why it's called base 10 is because we only have 10 symbols, and as soon as we add on one more item, so here I'll add on one more thing here, we don't create any new symbols to represent this amount. Instead, we use the idea of place value to regroup these into a new place value. And so these become, like, now we have one single block of tens, and we have 0 ones. And so we write the number 10 as 1, 0, but we're not creating any new numerals. And usually the way that we'll organize this is we'll do it with a place value chart, and we'll say, okay, we've got the ones column, and you look at how many ones do you have, which in this base 10 block set is represented with the yellow blocks. And then you say, how many tens do we have, how many hundreds, and how many thousands. And each one of these place values is basically 10 of the previous place value, because here I have 1 10, but if I were to have 2 tens, 3, 4, 5, 6, 7, 8, 9, 10 tens, that amount could be regrouped into 100. And so that creates this next place value. And then if I had 1, 2, 3, oh, this is going to go off the screen, but you get the idea that if you had 10 of those, it would make a thousands block, which would look like this. So that's the basic idea of our base 10 numeration system. And what you guys are going to be working on today is numeration systems with other bases. And there's only a couple questions on your homework that have to do with this, but I highly recommend you spend a lot of time working on them and make sure that you very thoroughly understand them, because later on in this course, we're going to be doing arithmetic with other bases, meaning we're going to be adding, multiplying, and I can't remember if we do division or not, but we're going to be doing at least addition and multiplication and subtraction with these other numeration systems. So I'm going to do, let's do base 4. So in this little applet here, and I'll give you guys the link to this so you guys can utilize this on your homework, I can change the base of my numeration system right here in the middle. So you select all of the blocks, and then you just click this arrow that changes the base. And since I'm doing base 4, I'm going to click it down to base 4. So the idea of how base 4 works is we're going to have 4 symbols that represent amounts. And I'm going to use the same symbols that we use in base 10 to help make this a little bit easier. So to start off, we have 0, which represents the idea of having nothing. And then we have the number 1, which represents having one thing. Then we have the number 2, which represents having 2 things. And then we have the number 3, which represents having 3 things. Now, these are the only symbols that we use in base 4, because base 4 means that we only use 4 symbols, and the rest of the amounts are represented with place values. So when we have 3 items and we add one more, and now we have 4 items, in base 4, we can regroup these into the next place value. And so the next number that represents the amount that we know of as 4 is represented with a 1 in the second place value and a 0 in the first place value. Then if we wanted to represent the number that we think of as 5, we would have 1 in the 4 column, or 1 in the second place value, which I like to think of as the 4's place value, because there's like 4 things in that block. And then we'd have 1 in the ones column. So what we normally think of as the number 5 in base 4 would be written as 1, 1, because we have 1 in each of the place values. Then if we have one number bigger than that, like because I'm counting in base 4, The number we think of as being 6 would be written as 1, 2, because we have 2 ones, and then we have 1 of the second place value, which I like to call the 4's place value, again, because there's 4 things in it. And if we kept on counting like this, so I'll add one more, this would be 1, 3. And then the next time I add one on, I have enough that I can regroup these into the next place value. So I would have 2 of these. So the next number would be 2, 0. And this number 2, 0 in base 4 is equivalent to what we would call in base 10 the number 8. Because you can see we have 8 blocks here. But the way that we're expressing it in this numeration system is 2, 0 because we have 2 of the second place value. And then if we keep on counting, here we've got one more here. So that amount would be expressed as 2, 1. If we count on one more, that would be 2, 2 and 2, 3. And there will be no 2, 4 because remember, we only have these 4 symbols. And the number 4 is, the numeral 4 is not included in the symbols that we're allowed to use. So as soon as I add on one more, then I can regroup these together. And the next number would be 3, 0. And I'm going to continue this for just a little bit longer. So I'm going to keep on counting on. So the next number would be 3, 1. And the reason I'm not calling it 31 or 30 is because I don't want you guys to mix it up with the base 10 number or numeral 30. Because in base 10, 3, 0 means that you have 3 10s and 0 1s. But in base 4, it means that you have 3 4 blocks and 0 1s. So just a clarification on that. So we'll keep on counting on here. So we have 3, 1. Then we have 3, 2, represents that amount I have on the screen. Then 3, 3 would be this amount. And the next amount that we have is going to move into the next place value because when I regroup these 4 1s into a 4 block, I now have 4 4 blocks. And remember, we can't use the symbol 4 when we're in base 4, just like we don't have a symbol that represents 10 in base 10. And so all 4 of these can be regrouped into the next place value. And so the way that we would write this would be 1, 0, 0. And that would represent this amount here. So in the base 4 place value system, the ones column is just the ones column. The second place value, though, is in base 10, we would think of it as being the 4's column because this block has 4 things in it. And then the next place value is the 16's column because you can see there's 16 blocks in here. And again, I'm using base 10 numerals to describe these columns just because we're most familiar with base 10. But in base 4, they would think about, like if you had another society or something that used base 4, they would think about it much like we think about like the tens and hundreds column, because that's what those numbers would be written as in their numeration system. But I'm going to write it out in base 10 numerals so that it's related to numerals that you guys are more familiar with. And we never counted up to this place value, but the next biggest place value would be 4 groups of 16. And if we multiply 4 times 16, that gives us the number 64. And so the 4th place value is the number 64. And you can figure it out just by taking the previous place value and multiplying by the base. So like in this case, the 1's place value times 4 gave us the 4's place value. 4 times 4 gave you 16. 16 times 4 gave you 64. Or another way you can do it is to use exponents, because the number 1 is equal to 4 to the 0 power. And the number 4 is equal to 4 to the 1st power. 16 is equal to 4 squared. And 64 is equal to 4 cubed. because basically with each place value, you're multiplying the previous one by another 4. And so the exponent just keeps increasing by 1. So that's the basic idea of how other bases work. So I'm going to talk about how we can convert from other bases to base 10, which we're more familiar with. So let me clear this. And let's convert base 6 to base 10. So I'm going to change all of these blocks to be base 6 so that we can visualize this as we go. Okay, so these are the base 6 blocks. And notice how these are different than the base 4 blocks because each of the second place value block, these green ones, have 6 blocks in them. And then if you have 6 copies of those, you get this next block, which would be 36 blocks. And then the thousands, well, it's not technically called the thousands, but the block that looks like a thousands block is going to have 6 36s in it, which means that it has 216 in it. So I'm going to write those numbers down in our place value chart just so that we can keep track of that. So the first place value in base 6 has 1 block in it. The second place value has 6 blocks in it. The third place value has 36. And the fourth place value has 216 blocks in it. And again, this is in base 10 numeration because in base 6, we don't actually have these symbols of 6s because we only have the symbols 0, 1, 2, 3, 4, and 5. When you're counting in base 6. But let's say that we had, I don't know, let's say that we have 2 of these red place values. So I'm going to draw pictures as I go. So let's say I have 2 of these. Let's say that I have 1 of these. And let's do 4 of the green and 3 of the ones. So this number, I'll represent it really quick. Got 4 of the greens, and then 3 of these. Okay, so this number in base 6, which I'm going to represent by writing the word 6 as a subscript, because that tells me what base it's in, and this is the same notation you'll see in your textbook as you're working on your homework. If we wanted to convert this base 6 numeral, remember that's the symbols that we're using to represent the amount that I've shown on the screen here. If we wanted to convert this into base 10, the easiest way to do this is to figure out how much is in each place value in base 10. So these red blocks, we calculated have 216 individual blocks in them because 36 times 6 is 216. So in base 10, these blocks are equal to the number 216. In base 6, they would be equal to the number 2000, which kind of looks like 2000. But I wouldn't call it 2000 because the bases are different. So in base 6, it's equal to this, but in base 10, it would be equal to 2 times 216 because 216 is the amount of blocks that we have in one of these blocks in base 10 numerals. And so I could say, okay, well, whatever 2 times 216 is, that's the amount that I have in just the red blocks. And then in the blue blocks, I would have 136 because those blue blocks have 36 cubes in them. And again, this is not the way that you would write it in base 6 because in base 6, you would write it as 100 because you have 1 of the 36 blocks and 0 of the 6 and 1 blocks. But in base 10, we would write that amount as 36 and we would multiply by 1 because we only have 1 of those blocks. And then for the next place value, it looks like we have 4 6s. So we could figure out in base 10 the amount by doing 4 times 6. And again, in base 6, it would look like 400, 40 for that amount. But in base 10, it would be 4 sixes. So we'd multiply by 6. And then the last place value would be 3 times 1. And that one is the same as base 10 because base 10 also has a ones column. And if you notice, this is basically the expanded form in the other base because we have 2 times our largest place value, 1 times our next largest, 4 times our next largest, and then 3 times our smallest place value. And to figure out what the entire number is in base 10, we just need to simplify this expanded form into a more concise form. So I'll get my calculator and let's do 216 times 2. That gives us 432 in base 10 numerals. So notice I'm not doing the subscript 6 anymore because if there is no subscript, you can just assume that it's in base 10. And then I would add on 1 times 36, which is 36. Then 4 times 6 is 24. And 3 times 1 is 3. And when I add all of these together, 432 plus 36 plus 24 plus 3 equals the number 495. And this is in base 10. You don't have to write that subscript because if it doesn't have a subscript, it automatically means it's base 10. But this number in our typical numeration system, base 10, is equivalent to this number in base 6. And I should actually be saying numeral. This numeral, or these symbols in base 10, represent the same number or the same amount as this numeral in base 6. And so that's how you can convert from another base to base 10. You basically look at what all of the place values would be, and then you expand the other numeral into its place values by multiplying each symbol in each place value by the amount in base 10 that that place value represents. So that's how you would convert base 6 into base 10. Now, let's talk about how we could do this in reverse. So let's say that we were given a base 10 number, like let's say 827, and let's say that we wanted to figure out what base 6 number this is equivalent to. And I should actually be saying numerals because 827 in base 10 is a numeral, meaning it's a symbol that represents the amount of 827 items. And if we wanted to convert this to a base 6 numeral, the first step would be to remember what the place values are in base 6. So in base 6 and in any base, the first place value is always the ones place value. And it represents the amount of having one thing. And then in base 6, the next place value is 6 because 6 ones can be grouped together into this next place value that's represented with these green blocks here. And then if I have 6 of those can be regrouped together into the next place value, which is 36 blocks. And then the 36 blocks can be regrouped, well, if you have 6 of them, they can be regrouped into the 216 place value. And you can keep going with this as well. So like if you had 6 216 blocks, those could be regrouped into, I think it's 1200 something, but let's figure out exactly what it is. So if I have 6 of those, that would be 1296 and the next place value. And remember, these numbers that I'm writing in these place values are all written in base 10, but these are equal to the number 10 or 10 base 6 or 100 base 6 or 1000 base 6. these would be the numerals that we would use in base 6 to represent these amounts here. But I'm just writing them in base 10 because that's the numeration system that we're most familiar with. And it's also the numeration system we're converting from. So if I want to change the number 827 in base 10 into base 6, I basically need to figure out how many of each place value I have in base 6. So remember the number 827 represents having 827 blocks. And so that amount needs to be broken up into these place values that we have in base 6. So when I look at the place values, I don't have enough blocks to make a 1,296 block. So we don't even have a picture of that because it's basically 6 of these blocks. That's what it would look like. And we don't have enough blocks in order to make that because we only have 827, and that block would require 1,296. However, I do have enough blocks to have a 216 block. So 827 will have at least one 216 block. And I'm going to take 827 and subtract the amount of blocks that I've already converted over into base 6. So far I've taken 216 of my 827 blocks and I've put it into this largest place value here, or at least the largest one that we have a picture of right now. And the number of blocks that I still have remaining is 611. So that's a big enough number that I can have another 216 block. So I'm going to represent that with this one. And I'm going to write down that 227 is equal to another 216 being added on. And I still have enough blocks that I could make yet another one. So I'm going to subtract 216 to see how many I still have left and add on this third block and record that in my number sentence. So notice that 216 plus 216 plus 216 does not equal 827 yet, because I still have, if I look at my calculator, I still have 179 blocks that I still need to convert into base 6. And since 179 is less than 216, I won't be able to add on any more of these red blocks. However, I can start working on the blue blocks because I have enough blocks that I could make a 36 blue block. So I'm going to put, I think I could probably do maybe 4. So I'm going to try that, and maybe I might be able to do more. But basically I'm going to subtract 36, then subtract another 36, another 36, and another 36. And it looks like I did that perfectly because now I have 35 blocks left. And I'm just going to write down that I have 4 36s. And I now have 35 blocks left to distribute or convert into base 6. So I'm going to move on to my next place value, which is the 6's column. And I should be able to do 5 of these. So there's 1, 2, 3, 4, 5. And the reason that I knew right off the bat that I could have 5 of them is because I have 35 blocks, and 5 of those green blocks is 30, because each one of them is 6, and 5 6s is 30. So I'll write that down, that I have 1, 2, 3, 4, 5 6s. And when I subtract those 5 6s, so minus 1, 2, 3, 4, 5, that leaves me with 5 1s. And so if I put 5 1s in my picture here and write that down, whoops, that gives me the expansion of the number 827 in the place values of base 6. And then I can just look at how many I have of each thing. So I say, okay, well, I have 3 216s. So I'll have a 3 in that place value. I have 4 36s. So I'll have a 4 in that place value. And I have 5 6s. And so that would be in that column. And then I have 5 1s as well. And so what that tells me is that the number 827 is equal to the number 3455 in base 6. So this numeral represents the same number of items as this numeral in base 10. And that's how you would convert from base 10 to base 6 in this case. But if you were converting to like base 4, the only thing that would change is instead of having 6s and 36s and 2 16s here, you would have 4s, 16s, and 32s. Oh wait, no, not 32, sorry. 64, because that would be that place value. So the place values change depending on the base, but the process should be the same when you're converting. And you're welcome to use this applet if you would like to help you understand that process visually. So I hope this makes sense. If you have any questions, please let me know.